Now I'm going to give a rigorous proof of the Taylor expansion theorem, which means if f as a function, if the nth order derivative exists at x0, then we have the following conclusion. This function can really be written as a sum of a series of polynomials plus little omicron of x minus x0 to the power of n. This little omicron means this is an infinitely small amount, even smaller than this quantity. And this Taylor polynomial is a notation of the following sum of a series of polynomials. If the kth polynomial, kth order derivative at x0 over k factorial times x minus x0 to the power of k. K goes from 0 all the way up to n. Well, we will just prove by mathematical induction. So, first of all, when n equals k, n equals 1, is it true? Right? Can it really be written as the following? So let's check. So f of x, is it equal to t of 1, right? First order Taylor expansion. Let's denote this as the called Taylor series, right? Taylor series of nth degree of n, right? Degree of 1, what is it? So from 0, right? So from 0, 0, 1, 0 factorial 1. F of the 0th order derivative, that is the function itself, f of x0. All right, power of 0 is just 1, right? So plus the next one is the first order derivative, f dash of x0 times x minus x0. Plus little omicron of x minus x0. Is it true? Right. We just move this term over there and divide everything by x minus x0. F of x minus f dash of x0. Oh, sorry, there's no dash. Right? Just f of x0. Right. Move this term over there and divide everything by x minus x0. Right. So on the right hand side, I just have f dash of x0 plus little omicron of just 1, right? Just like doing normal algebra. Is it true? Right. So right hand side as x approaches x0, right? So nearby x0. So this is exactly the definition of the first order derivative at x0, right? Which is this one, right? Little omicron of 1, meaning approaches 0 as x approaches x0. It's really true. Really true. Right? So this expansion is true when n equals 1. How about let's assume that this is true when n equals k. In other words, f of x can be written as t sub k of f x x0, because the Taylor series only has to do 3 things, right? First of all, our function is denoted as f. Variable, we use x. At which point? At point x0, just random arbitrary fixed point. So plus little omicron of x minus x0 to the power of k. Right, this is our assumption. So we assume it's true when n equals k. We want to prove it's also true when n equals k plus 1. So we want to prove the following. F of x, is it equal to Taylor series of degree of k plus 1 of f x at x0 plus little omicron of x minus x naught is the power of k plus 1, right? We want to show the following equation. In other words, we want to show that can we move this term over to the left-hand side and divide everything by x minus x naught to the power of k plus 1. And we're left with just little omicron of just 1 on the right-hand side. Can we show that, right? So in other words, we just have to show f of x after we minus t sub k plus 1 of f x x naught. Then we divide everything by x minus x naught to the power of k plus 1. Is it equal to little omicron of just 1, right? So in other words, is this quantity infinitely small as x approaches x naught, right? So let's tk plus 1. So what is the Taylor series of degree of k plus 1? Right, sum k from 0 all the way to maybe I from 0 all the way up to k plus 1. Right? Just changing the index. So as x approaches x naught, a lot of terms will just approach 0. Majority of the term will just approach 0. And the only thing that's not approaching 0, let me see. So let's let x approaches x naught. As for Taylor expansion of degree of k plus 1, the first term, what is it? Let's double check. tk plus 1. Let's just expand it out. So f of x naught plus f dash of x naught times x minus x naught plus 2 factorial f double dash of x naught times x minus x naught to the power of 2 plus all the way up to k plus 1 factorial f the k plus 1th derivative of x naught times x minus x naught to the power of k plus 1. Right, that's a Taylor polynomial. So as x approaches x naught, the majority of the term will just approach 0, right? This term, this all the way to this term, they just all approach 0, except for first term, right? So t sub k plus 1 will, well, you know what I mean, right? T sub k. So we'll easily approach f of x naught as x approaches x naught. So which means if we look at the numerator, right? F of x minus this quantity, right? And this quantity already approaches f of x naught as x approaches x naught. And as x approaches x naught, f of x also approaches f of x naught because it's easily verifiable that the function is continuous at x naught, right? From our assumption, we assume that the nth order derivative already exists. Therefore, it's easy for us to verify that the first order derivative also exists, which means the function itself is continuous at x naught. Now, the top easily approaches 0 as well. Bottom also approaches 0. So 0 over 0 undetermined. We can use L'Hopital's rule again. All right, so I've just proven that this quantity is still a 0 over 0 type. So using L'Hopital's rule, we have differentiate the top. We have f dash of x, right? Minus the derivative of this Taylor polynomial of degree of k plus 1 is written like this. So differentiate this whole thing. What is it? constant, gone. Constant times this polynomial, easily the constant. So we have minus bracket f dash of x naught. Right, that's my first. And differentiate this one, right? 2 and 2 cancel out. And I'm left with using the chain rule. So plus f double dash of x naught times x minus x naught. Let's write one more term, right? The next term is 3 factorial at the bottom and to the power of 3, right? That's my polynomial. So using the chain rule again, we have imagine there is take down the power 3, and 3 factorial simplified down to just 2 factorial at the bottom, right? So I have 2 factorial at the bottom and f third order derivative at x naught times x minus x naught to the power of just 2. Perhaps let's just write one more term. Next term is imagine the bottom have 4 factorial, right? And x minus x naught to the power of 4, and take down the 4. 4 factorial, 4. Cancel, simplify down to 3 factorial at the bottom, right? Top, that is the 4th order derivative at x naught. X minus x naught to the power of 3 plus. All the way up to last term. Right, take down k plus 1, simplify down to just k factorial. Right, just k factorial at the bottom. F k plus 1th order derivative at x naught times x minus x naught to the power of k. Right? That's the top, right? So f minus bracket, this plus that all of the bracket. This at the top. At the bottom, what do I have? So what's the derivative of the bottom? Right? So k plus 1 times x minus x naught to the power of k, right? So this is my numerator, this is my denominator. I find out the limit of this whole thing. And remember, we assume that when n equal k, it's true, right? It can be written like this. In other words, let's rewrite it into f of x minus t sub k of f x x naught over x minus x naught to the power of k is equal to little omicron over 1, right? They're equivalent. That's our assumption. Now, in other words, if we observe closely, if we treat, look, even though the factorial does not match with the order of the derivative, right? They just differ by 1. We wish they were the same, but they are not. But in fact, if we observe closely, f dash x, right? F dash x, that's the first order derivative function of f of x. Let's just, it's also a function in its own right, right? So we can denote it as g of x, right? Even though it's a derivative, but it's still a function. So denote it as gx. So in other words, the f double dash of x naught is equal to the g dash of x naught, right? Because this is the second order derivative at x naught, which means to I just have to differentiate both sides on, right? This side, right? Differentiate this side, I have second order derivative of f. Differentiate this side, I have the first derivative of g. And if we fix the variable, that's the second order derivative at this point, is equal to the first order derivative of g at the same point. Right? Likewise, f the k plus 1th order derivative at this point is equal to the kth derivative of g at the same point, right? So this is clear. Now I can rewrite this numerator as the following. As f dash x. F dash of x, like I said, denoted as g of x minus quantity f dash x naught. Right? F dash x naught is equal to g of x naught. Right? Plus f double dash equal to g dash of x naught. Right? G dash x naught times x minus x naught. What's the following? F third order derivative, like I said, is equal to the second order derivative of g. Right. G double dash bottom, that's 2 factorial. At x naught times x minus x naught to the power of 2. All the way up to the last one is k plus 1th derivative of f is equal, like I said, to the kth derivative of g. Right? K factorial g kth derivative at x naught times x minus x naught to the power of k. Bracket. Right, so this is my numerator. Denominator is k plus 1 times x minus x naught to the power of k. Right? Now, so this should look very familiar. So g of x naught plus g dash x naught plus all the way up to this one is exactly the Taylor polynomial denoted as replace f with g, right? Taylor polynomial of degree of k with respect to function of g, variable x at the point x naught, right? So can be really written as g of x minus Taylor polynomial of degree k with respect to the function of g using the variable of x at x naught, right? Over k plus 1 times x minus x naught to the power of k. Using our assumption, right? I've rewritten our assumption into the following. F minus tk, f x over this is an infinitely small amount. The only difference here, I use f, there I have g, right? Same thing, same Taylor polynomial, same degree Taylor polynomial, same variable x, same point x naught. The only difference is f there. Here I have g, right? Bottom is same. The only difference is here I have k plus 1 as a constant. So, using our assumption, this is already infinitely small, which means this over that is infinitely small times a constant at the bottom, still infinitely small, towards tending towards 0 or equal to little omicron of 1. Same thing, right? Infinitely small as x approaches x naught, right? So which means I'm done, right? So remember, I want to prove this equal to that, which means I need to prove this is infinitely small. Using L'Hopital's rule, using the assumption, I've really shown that the limit of that, which is the limit of this, is really infinitely small, really 0, tending towards 0. Really true, right? Really tending towards 0 as x is closed enough to x naught, which means this is really true, right? Proven this, proven that, this is true. So it's really true when n is equal to k plus 1, really true, based on our assumption n equals k, it's true, right? We've also proven it's true when n equals 1. So according to the mathematical induction, it's really true for any positive integer n, right? Function can really be written as a Taylor expansion plus Peano remainder.